Good morning children and welcome back to your chemistry class. Today in this chapter of isomerism we are going to study about stereoisomerism, and as I had told you earlier, stereoisomerism is of two types, geometrical isomerism and optical isomerism, that we are going to study. So first and foremost, let us understand what is stereoisomerism. So when same molecular formula represents two or more compounds, okay, which differ in the spatial arrangement of atoms or groups. Such compounds are called stereoisomers, and the phenomenon is termed as stereoisomerism, right? And then they are of two types, geometrical isomerism and optical isomerism. Let us begin with the first one, that is geometrical isomerism. So when the same formula represents two compounds which differ in their spatial arrangement of atoms or groups around the carbon double bond, right, then such isomers, they are termed as geometrical isomers, and the phenomenon, what it will be called as, geometrical isomerism, right? So let me write down when this one I'm talking about, when the same molecular formula represents two compounds which differ in the spatial arrangement of atoms or groups is called geometrical isomers, and the phenomenon is termed as geometrical isomerism. Okay, this point is clear. Now this is due to the restricted or hindered rotation around the double bond. The isomer in which two similar atoms or groups are on the same side of the double bond, what are they called as? Cis isomer. What did I say about cis isomer? Two similar atoms or groups on the same side, okay, then they are termed as cis isomer. For example, you can take like this: carbon, double bond carbon, this is B, then this is also B. Two similar atoms on the same side. If this is A, then this is also A. This is your cis isomer. Followed? Now let me talk about the next one, that is the trans isomer. Now trans isomer, when two or similar atoms or groups, they are on the opposite sides of the double bond, okay. Two similar atoms or groups on the opposite sides of the double bond, same side of the double bond, okay. So this could be like, we can draw it like this: carbon, double bond carbon. Okay, if this is A, then this side it will be B. If this side it is B, then this side it will be A. So this is your trans isomer. I hope till here it's very clear. Now I'll give you some more examples of cis isomer and trans isomers. Let us observe the geometrical isomerism in oximes and azo compounds. Okay, so first I'll show you for oximes. So let's see over here first, carbon double bond N. This is your oxime, okay, where here you have the lone pair. This is your OH group, this is your H, and this is your C6H5. So this, due to restricted rotation around carbon and nitrogen, oximes, they show geometrical isomerism, right? Now especially in case of oximes, here it is going to show you sine isomer. Now sine isomer is an analogy of cis. It is used for the word cis, right? It is one in which you can see the hydrogen atom and the hydroxyl atom, or the OH, they are on the same side of the double bond. Clear? But in anti-isomer, that is another analogy of your trans isomer, you will find, let me show it to you over here, NH, here it will be OH, the lone pair will be here, this is C6H5, and here it will be H. So this is called as anti-isomer, and both the name will be what? This is syn-benzyl doxime, okay, and this is your anti-benzodoxime, and this is an analogy for your trans isomer. So over here, have you understood where you will see in the trans or an anti-isomer, the hydrogen and hydroxyl group, the OH, they are on the opposite sides of the double bond, right? Similarly, now let us talk about azo compound. For azo compound, let me draw it over here. It is N double bond N, okay? So here you will see the lone pair, here you will see the lone pair. Here it is C6H5, here it is C6H5. So this is what? This is your syn-azo-benzene, right? And syn-azo-benzene means cis, where both the sides you will see the similar group or atom. Now let us see anti-isomer or anti-azo-benzene. So N double bond N, the lone pairs will be on the opposite side, and the atoms also, or the group, will be on the either side of the double bond, C6H5. This is your anti-azo-benzene. Clear? I hope this is very clear to you. Now, what are the conditions that are necessary for geometrical isomerism? Firstly, the molecule must have a double bond. Molecule must have a double bond. First point is clear. And second, there must be two different atoms or groups attached to each carbon atom of the double bond. Okay. There must be two different atoms or groups attached to each carbon atom of the double bond. So these are the two conditions necessary. Now, what are the characteristics of geometrical isomerism? The geometrical isomers, they have different physical properties, but identical chemical properties. Okay, and stability of the two isomers, they are absolutely different. For cis and trans, they are very different. Trans isomer is more stable than cis isomer. I hope this point is also very clear. Begin with an example over here. So I take the first example, C2H2Cl2. What is this also called as? 1,2-dichloroethene. Okay, so let's see both the cis isomer and the trans isomer of this particular compound. So carbon-carbon double bond is a must, and if I am drawing cis, then what? Both hydrogen should be at one side and both chlorine on the same side of the double bond of the carbon atom. So this is your cis 1,2-dichloroethene. Now let me draw the trans. Carbon-carbon. Okay, this is hydrogen, then here it will be chlorine, here it is going to be chlorine, then here it is hydrogen. This is your trans 1,2-dichloroethene. I hope this is very clear to you. Let's take one more example of malic acid and fumaric acid. So here carbon-carbon double bond, both COOH, COOH, this is H and this is H. So what have I formed? This is my cis malic acid. Now let me form the trans, and the name changes to fumaric acid. So carbon-carbon double bond, here it is H, then here it is COOH, here it will be COOH, then here it is H. So what is this? This is your trans isomer, which is called as fumaric acid. I hope it is very clear to you. So this we can also say it as cis butene 1,4-dioic acid. What is the name of this? Cis butene 1,4-dioic acid, whereas this is trans butene 1,4-dioic acid. Okay. Now, how can we find the number of geometrical isomers in alkenes? Let's see that. So first point, if alkene has only one double bond, then the number of geometrical isomer will be 2 to the power of n. Now n over here stands for number of double bonds, right? So for example, if there is one bond, so 2 to the power of 1, that means how many isomers does this particular compound contains? It contains only 2. 2 to the power of 1 means it is 2. So only 2 isomers, geometrical isomers are present in the particular compound. For example, let's see CH3, CH double bond, CH, CH2, CH3. What is the name of this? This is your pent-2-ene. Right, now I want to know the number of geometrical isomers present over here. So use your formula. How many double bond? 1 double bond, 2 to the power of 1. That means 2 geometrical isomers are present over here. Right? Suppose there are 2 double bonds, then 2 to the power of 2. That means 4 geometrical isomers are present in the particular compound. I hope this point is very clear to you. Now, if along with a double bond, if an asymmetric carbon is also present, then both geometrical and optical isomerism will be observed. Now, optical isomerism, I'll be explaining it to you after this, but just would like to tell you that if there is a double bond present and there is asymmetrical carbon atom also, then both geometrical and optical isomer will be found over here. Right? So for example, you can see this CH3, CH double bond, CH, CH, Br, CH3. Right? So now this is going to show you what? This is showing you your geometrical isomerism, okay? And this whole lot, what is this showing you? This is showing you optical isomerism. Optical isomerism. Over here, how to find out number of optical isomers or number of geometrical isomers? Use the same formula. So how many number of geometrical isomers are over here? 2 to the power of n, 2 to the power of 1, which is 2. This is the number of optical isomer. Okay. Number of geometrical isomer, if you need to find out, 2 to the power of n, which is 2 to the power of 1, which is 2. So in total, how many total number of isomers are there? Total number of isomers are how many? 4, where you will find 2 optical isomer and 2 geometrical isomer. And when is this possible? That when along with the double bond, if there is an asymmetric carbon also present, then you have both geometrical and optical isomerism found over here. I hope this point is clear. Okay. Before I move to optical isomerism, one more point I would like to emphasize over here, that if alkene has more than one double bond in such a manner that the ends are different, then the geometrical isomerism formula that you are going to use will be 2n only. Okay. When did I say? When the ends are different and the compound has more than one double bond. Clear? Like for example, in your hepta 2,4-diene. Now here if I draw it, CH3, CH, double bond, CH, CH, double bond, CH, CH2, CH3. So here what do you see? Here the end are the same, CH3, CH3. So here you are going to use the formula 2n square. But if there is more than one bond and its ends are not same, then the number of geometrical isomers, you have to use the formula 2n minus 1 plus 2b minus 1. Okay, where your b is equal to n upon 2 if your n is even number, right? And b will be n plus 1 upon 2 if your n is an odd number. Is that clear? And what is n? I hope you know that, the number of double bonds. So this formula is to be used when the ends of a compound which has more than one double bond are not same. But if the ends are same and more than one double bond, then we are going to use 2n, 2 to the power of n as your formula to find out the number of isomers. Okay. Let me give you one example. For this example is very clear. Now I'm going to give you one such example where the ends are not the same. So CH3, CH double bond, CH, CH double bond, CH, CH3, right? So over here, now see 2 to the power of 2 minus 1 plus 2 to the power of 2 upon 2 minus 1. So what is it going to give us? 3, right? Why so? Because n over here is your even number. So before we understand what is optical isomerism, let us understand what is plane polarized light. In the ordinary light, the vibrations, they occur in all planes perpendicular to the direction of propagation, and this is called as unpolarized light, right? But when this light is passed through a Nicol prism, all vibrations except those in one particular direction, they are cut off, and the plane polarized light is obtained by the total internal reflection. Okay, I repeat, now I'll show it to you with the help of a diagram also. Now suppose this is your ordinary light. suppose this is your ordinary light, okay, and suppose this is your Nicol prism, okay, Nicol prism. Then the light which passes by, which one? All vibrations except the one in one particular direction, they are cut off, and the plane polarized light is obtained by the total internal reflection. Is that clear? So this is called as your plane polarized light, right? Now, what is optical activity? The property of a substance to rotate the plane polarized light through a definite angle, that is called as the optical activity. And such substances, they are called as optically active substances, okay. So the property of a substance to rotate the plane polarized light through a definite angle is called optical activity. Is that clear? And such substances, what are they called as? They are called as optically active substances, right? Now, next word that we need to understand over here, polarimeter. What is polarimeter? The rotation of the plane polarized light by an optically active substance. It is always measured by a certain instrument. What is that instrument called as? This is called as polarimeter. Okay, so the rotation of the plane polarized light by an optically active substance is measured by an instrument called as polarimeter. Followed, then we come to another word, specific rotation. Now, what is the formula for specific rotation? It is always written like this. Okay, this is specific rotation. It is equal to observed rotation upon the length of the substance in decimeters into concentration. Okay, this is the formula that you should learn. A few numericals are based on this, right? So what does this specific rotation mean? Specific rotation is equal to the observed rotation in degrees upon the length of the solution in the decimeters into the concentration of the substance in grams per centimeter cube. Okay, whereas here what do we mean by D? It is the wavelength of the light that is used over here, and T is the temperature, generally 25 degrees Celsius. Wavelength of light that is used over here, D, which is used over here, is 5893 Armstrongs. This is the wavelength of the light which is used here, and the temperature over here is 25 degrees Celsius. Okay, so what is the cause of this optical activity? The optical activity of the substance, it is due to the presence of dissymmetry or chirality in the molecules. Now, when an object is non-superimposable on its mirror image, then it is called as what? Chiral, right? Like for example, pair of shoes or your gloves or your hand, like when you superimpose your hand one over the other, they are non-superimposable, right? One thumb is this side and the other thumb is this side, but though they both are of the same work, right? Then they are termed as chiral. So the objects which are superimposable on their mirror image, they are called as achiral. What they are called as achiral. For example, a sphere. A sphere, if you keep it in front of the mirror, it is going to give you the superimposable image. So that is called as achiral. But the ones which do not give you the superimposable image, if placed in front of the mirror, then they are called as chirals. I hope this is very clear. Now, what is the origin of this chirality? So Van 't Hoff and Liebel, they showed that the origin of chirality in organic compound, it is due to the tetrahedral nature of carbon. Okay, it is due to the tetrahedral nature of the carbon. That is, when a carbon atom is attached with 4 different atoms or groups, the molecule obtained, it always shows a chiral molecule, and the property that is possessed by it, what is it called as? Chirality. This is suppose Br, this is suppose F, and this is suppose Cl. So now what do we see over here? A carbon atom, it has 4 valencies, right? And they are satisfied with 4 different atoms or groups, right? And they are asymmetric carbon atom, or this is called as a chiral center. This carbon is called as a chiral center because 4 different atoms are attached to the carbon, right? So this carbon, what is this carbon called as? Asymmetric carbon. I hope this is very clear to you. Next we talk about, let us begin with the enantiomers, right? So what are enantiomers? The stereoisomers, which are the non-superimposable mirror images of each other, they are called as enantiomers. And they could be, for example, D-lactic acid or L-lactic acid, as I told you, dextrolactic or leolactic acid. Now, I was talking about the properties of enantiomers. So, as I told you, they have identical physical properties. Identical physical properties like melting point is same, right? Boiling point is same, density will be same, and so on. Then they differ in the action towards, they differ in the action towards plain polarized light. Okay, then they have different biological properties. They have different biological properties. Then even they have identical chemical properties. The rate of reaction, however, is different with the other optically active reagents. Okay, they have identical chemical properties with different rate of reactions with other optically active reagents. I hope this is clear. Now we talk about some of the elements of symmetry. Now, what are the elements of symmetry? The elements of symmetry are plane of symmetry and center of symmetry. Okay, So what do we mean by plane of symmetry? A molecule is said to have plane of symmetry if it has a real or imaginary plane which when passed through molecule, it bisects that part one half of the molecule, right? It is just like a mirror image of the other half. Like for example, you can see this COOH, CCH3OH and H. Okay, so this shows the plane of symmetry, and this is an example of your lactic acid. Now, what is center of symmetry? Molecule is said to have a center of symmetry when it contains an imaginary point from which lines, when drawn on one side and extended an equal distance on the other side, will meet the identical points in the molecule. For example, if I draw it over here, see if they are drawn from here, right? So they are extended at equal distance on the other side and they meet at the identical point in the molecule, the identical points in the molecule, right? So this is an example of trans 1,3-dibromo-2,3-dichlorocyclobutane. Only that molecule which possesses neither plane of symmetry nor center of symmetry, that is your chiral molecule. Okay, that is your chiral molecule, which is also called as dissymmetric molecule. Okay, so chirality, it is regarded as the necessary and sufficient condition for a molecule to be optically active. I hope this point is clear to all of you. Now talking about your optical isomerism. So let us understand what is optical isomerism. So when two or more compounds having same molecular formula, similar chemical structures, they exhibit different effect on the plane polarized light, the phenomenon what it is called as optical isomerism, and the compounds, they are called as optical isomers, right? And these are optical isomers, they are of two types. What are they? D isomer and L isomer. What do we mean by D? Dextrorotatory. What is D? It is dextrorotatory or D isomer, and L is levorotatory or L isomer. Now, dextrorotatory or D isomer, these are the enantiomers which rotates the plane polarized light to the right, or what we can say to the clockwise direction. Then they are called as dextrorotatory isomers. But if the enantiomer which rotates the plane polarized to the left or to the anti-clockwise direction, then it is called as levorotatory isomer, right? Next we come to another new word, that is racemic mixture. Now what do we mean by racemic mixture? This is, we also write it as DL, or we also write as this mixture. Now what do we mean by DL? When the mixture contains equal amount of dextro and leo isomers of the substance. Okay, what did I say? Mixture containing equal amount of dextro and leo isomers of a substance, then they are termed as racemic mixtures or DL mixtures, which are also denoted like plus minus, right? It is optically inactive. This is optically inactive. Why? Because the rotation caused by one enantiomer is exactly compensated by the one which is caused by the other enantiomer. So this phenomenon is also termed as external compensation. What is it also called as? External compensation. So again I repeat, what is racemic mixture? Mixture containing equal amount of D and L isomers of a substance. Then they are termed as racemic mixture, also written as DL mixture or denoted with plus minus sign, right? They are optically inactive. Why? Because the rotation caused by one enantiomer is completely compensated by the one that is caused by the other enantiomer, and this is also termed as external compensation. Now what is racemization? What do we mean by racemization then? The process of converting D form or L form, right, of an optically active substance into a racemic mixture. This is called as racemization. What did I say? The process of converting D form or L form of optically active substance into the racemic mixture. This is called as racemization. Then what is resolution? What do we mean by this word resolution over here? The process of separating or separation of the racemic mixture into your D and L component, that will be termed as resolution. Okay, so the process of separation of a racemic mixture into D and L components, right? This is called as resolution. Now we come across another compound which is called as mesocompounds. Now what are mesocompounds? Those compounds which are optically inactive in spite of the presence of asymmetric carbon, as the molecule contains plane of symmetry and this lacks chirality. Then they are termed as mesocompounds. Okay. Compounds which are optically inactive in spite of the presence of asymmetric carbon, as the molecule contains plane of symmetry and thus lacks chirality. Okay, rotation caused by the upper half of the molecule is equal but opposite to that caused by the lower half of the molecule, and it is compensated by one another. So for example, I am showing it to you over here of a mesotartaric acid, right? CHHCOOH, right? And this is similar to CHHCOOH. Now look at this, right? This goes like this. So this is your plane of symmetry, right? So it is optically inactive. Why? Due to internal compensation. Why? because of its internal compensation, right? This is an example of your mesotartaric acid. I hope this is clear. About optical isomerism in lactic acid, right? Lactic acid, it has one asymmetric carbon atom, right? And therefore it exists in two forms. What are those two forms? One is your D form, dextrorotatory, that means it rotates the plane polarized light in the clockwise direction. And next is your L form, that is it rotates the plane polarized light to the anti-clockwise direction. And when D form and L form, they are mixed in equimolecular proportion, then racemic form is obtained, which is optically inactive. Okay, so for example, if you see over here, COOH, CH3OH, H. Okay, this is your asymmetric carbon, right? And now see here, so this one is your D, or you may say the plus lactic acid, right? Its melting point is 26 degrees Celsius. This is your L form, or you may say the negative lactic acid, and over here also the melting point is 26 degrees Celsius, right? Now let's also talk about tartaric acid. The optical isomerism in lactic acid I showed you. Now optical isomerism in tartaric acid. It has two asymmetric carbon atoms. Two asymmetric carbon atoms, right? So what does it mean? That it exists in three forms. What are those three forms? They are your D form, L form and mesoform. Clear? So it means D dextrorotatory means it rotates the plane polarized in the clockwise direction. This rotates the plane polarized light towards the anti-clockwise direction. And meso, it is optically inactive due to the presence of your plane of symmetry in the molecule, and this also shows internal compensation, right? So when equimolecular proportions of D and L forms is mixed in racemic form, the plus minus mixture, or you may say the DL racemic form mixture is obtained, which is optically inactive due to external compensation, right? So I can show it to you over here. COOH, COOH. This is, so here you can see the two asymmetric carbon atoms. So this is your D-tartaric acid, okay, and this is your Leo rotatory tartaric acid. Now meso tartaric acid, let's see this one, COOH. So over here we will see this. This is what your plane of symmetry. Plane of symmetry, right? That is the zero net rotation you are going to see. Plus and minus over here. Okay. And this shows your mesotartaric acid or superimposable mesotartric acid. They are the stereomers that are not enantiomers or are not mirror images of one another, and they have different chemical properties also, right? They have different physical properties also. They have identical configuration about one chiral carbon, but mirror image configuration about the other chiral carbon. Like for example, if you look at the structures 1 and 2 and 3 and 4, they are pair of diastereo isomers, right? Similarly, 1 and the 4th one, if you see, and the 2nd and the 3rd one, these are the diastereomers. Again, I repeat, what are the diastereomers? These are those stereoisomers that are not enantiomers, and they are not the mirror images of one another. Okay, like see in 1 and 3, what do you see? Here you will see the identical configuration about one chiral carbon, and here you are going to see the mirror image configuration on the other chiral carbon, right? Similarly, in the 2nd and in the 4th one also, here you will see the identical configuration of one chiral carbon, but in this one you will see the mirror image configuration. Is this point clear? Again, go back to your images and see once again. Again, I have to tell you D-tartaric acid or L-tartaric acid and mesotartric acid. They are the diastereo isomers, either D-tartaric with meso or L-tartaric with meso. They are the diastereomers. So what are the characteristics of these diastereomers? A pair of enantiomers, they have similar chemical properties. Their chemical properties are not identical, react with a given reagent at different rates, right? Then pair of diastereomers, they differ from one another in their physical properties. They can be easily separated from one another by fractional distillation or crystallization, or even by chromatography. Then these diastereomers, they have rotation in the same direction but to the different extent. They may have rotation in the opposite direction in the same cases, right? So with this, we finish off with the isomerism. Thank you.